deflection of charge. Deflection of charge. Till now what we studied, basically a charge is moving in a magnetic field. We applied our right hand thumb rule, everything. We found out how to find out the direction of the charge and so on and so forth. But now we have to find out the deflection. We know it will move in this direction. We know if the magnetic field is inside, charge is thrown here in this region, it is going to have a deflection. But now we need to find out what will that deflection exactly be. What will the deflection exactly be? So let me read out one small thing. Okay, the statement is a particle of mass m and charge q is projected in a region with a width of d which is perpendicular to the magnetic field b. So this statement is simply saying that there is a magnetic field. 1 minute. There is a magnetic field which is inside the board like this, and the thing here, the observer is telling here is that this magnetic field is having some width, and that is denoted by d. But there is a charge right over here. Let's say that q. Okay, that charge is there. It looks like a lambda here. Sorry. 1 minute. Let's say that the charge here is q. In that case, what will happen if it has a certain velocity vector here? Can I say that it will deflect? Yes or no, students? Give me a response. All of y'all. Okay, it will deflect. So if it is deflecting, it should produce a circular path, as we had seen earlier. It should produce a circular path. But what if I tell you that I have restricted the region where magnetic field is present? If in that case, if I have restricted it only to a width of d, and I'm saying that this charge has been flicked, okay, I've flicked it with a certain velocity, and it is having some circular path. It is going towards that. It is trying to form that circular path. But when we talk about a circular path, of course, every circle has a center point, and from the center point to the circumference is called a radius. So if it is anyway going to form a circular path, I can say that the center point of that circle can be somewhere here, and this entire thing can be taken as a radius. So students, if this is entirely the radius, and the thing is the region of the magnetic field is restricted to a certain limit, then will my charge be able to form a circular path? Will it be able to form a circular path? Is it possible?
No.
It won't be able to form, because for it to produce a circular path, it needs to have magnetic field everywhere. In that way, it will get a force at every path, at every point of the path. It will have a force inside the center of the circle. But right now, let's just consider it has a certain velocity v, and it is going like this. It travels only till this path. So can I say, okay, it travels only till this path, and after this, what happens to it? It escapes. Okay, my magnetic field is restricted only till this direction. That means at this point, it is not having any force towards the center of the path. It's not having it is at this point, there is no radius of curvature here. It escapes. Okay,
Sir,
so yes.
Sir, suppose if there is no restriction, then would it form an entire loop?
Yes, it will form an entire loop. We had done that in the earlier lecture, isn't it? So I showed you that if this is fully, okay, if this is entirely covered like this with a magnetic field which is inside the board, and I'm flicking this charge over here with some certain velocity vector v over here, then what will happen? At this point, it will have a force inside. At this point, it will have a force inside. This point also, it will have a force inside. That way it completes the entire circle. But here I'm telling that I have restricted this entire magnetic field here. I have removed this region here. I have removed it, and I have made sure it's only covering this much, this part. So at that point, I can say that when this same thing over here, I'm showing it here. So when the charge is being flicked with a certain velocity and it does not have magnetic field any further, it will escape. It will escape the region, and it escapes the region with some velocity v. And if it is escaping with some velocity v, then of course it is going to make an angle, and this is what we need to find out. That's the topic, deflection of charge. Students, this is an important topic. This is called deflection of charge, and we are now interested at what angle is basically this charge escaped. Students, this is the same concept used in gravity as well, but you can think of it as a rocket being launched, and finally we try to these are the same concepts in different variables. Okay, so try to understand the concept now. So if we know that it is escaping at a point here, students, can I say that the escape point here is same as the width d? Can I say this width d is the same thing over here? It is escaping at this point, so this d is same over here. Yes or no? In that case, students, can you tell me if this is the radius r, from here to here is the radius r, then what will be the radius at this point? What will this be? Can you tell me what will this be? What will this be? What
R.
will this be? Wrong. See, look here. Now this is where you have to understand. If this is theta, can I say this is also theta? If this is theta, can I say this is theta? Yes or no? So in that case, if I have to find out the r component in the horizontal direction like this, then I have to take what? I have to take the component of it. Okay, yes or no? Yes or no? So
Yes, sir.
what will be my r over here? It will be r sine theta. What it will be? R sine theta, because I am not interested in this. I am not interested in this. I am interested in the distance here. This. Okay, you will tell me, sir, this is r cos theta. This, yes, of course, this is r cos theta. But what is this then? This is r sine theta, and it is equal to what? The width d. Is this clear, everyone, students? I want to make this clear. Is this clear? Students, is this clear?
Yes, sir.
All of y'all? All of
Yes,
y'all?
sir.
Okay. So we know that r sine theta is going to be equal to the width of the magnetic field d. In that case, what is sine theta? Sine theta is simply d by r. Students, sine theta is d by r. But students, in the lecture in the morning, or not only in the lecture which we had done in the morning, previous lecture also, do you remember what is the radius of the curvature of a charge in a magnetic field? What was the radius equal to? Radius was equal to what?
MV upon QB.
mv upon
MV
qb.
upon QB.
Yes, but in case you forget it in the lectures after that, how would you find out? Simply, you know that you have to relate kinetic energy with the force on a charge. So you know that F is equal to what? Q V cross B. Okay, and you also know that K E is equal to half mv square. Okay, K is equal to half mv. Sorry. Yes. So Ke is equal to half mv square. So using these two relationships, you can basically find out what the radius of the curvature will be. R is equal to mv upon qb. But now, if we know, without wasting much time, because I have to further many concepts, we know that R is going to be equal to mv upon qb. And if mv upon qb is the radius, substitute it here. What will you get? What will you get, students? What will you get? Sine theta is equal to what? Sine theta is equal to what? Will you get q b d upon mv? Will you get this? QBD upon mv?
Yes, sir.
In that case, students, theta will be what? Theta will be sine inverse of QBD upon mv. QBD upon mv. This is called the This is called the deflection of charge. This is basically the angle. This is the angle at which our charge is going to escape. Okay, if the magnetic field is limited. Okay, a quick summary, students. A quick summary. Okay, so what I said is basically the width of this magnetic field is smaller. What I said, the width of this magnetic field here is smaller than the radius. At that at this condition, in this condition, what is going to happen is your charge is not going to be able to complete the entire circular path. It will escape at some certain point as soon as the magnetic field is over. So at that point, it will escape with some velocity. But now we are interested in the topic of deflection of charge. So how to find out what is going to be the deflection of charge? Simple. You know this is R. If you know the vertical component is R, then the horizontal component, of course, is going to be R sine theta. But R sine theta, you can see in this diagram, is also equal to the width of the magnetic field. And so if it is equal to the width of the magnetic field, you can write R sine theta equal to D. You can equate them. In that case, sine theta, you can find out theta, sine theta, just rearrange the term, sine theta equal to D upon R. And then theta equals to sine inverse of QBD by MV, because R is equal to MV by QB. Substitute the value of R in place of in this capital R, and you will get the result theta equal to sine inverse of MV QBD upon MV. So if this is clear, students, let's come to some interesting questions. Interesting questions based on the same concept. So here the question states, find the angle. Again, it is about finding the angle of deviation of a particle if it comes out of the magnetic field. Okay, the question is, find the angle of deviation of the particle as it comes out of the magnetic field if the width d of the region, if the width of the magnetic field is slightly smaller, very slightly smaller than mv upon qb. Okay, so he's telling that we have to find out what the angle of deflection is going to be if at all my radius is slightly smaller than mv upon qb. Okay, so students, before we try to solve this, the first thing is, first we should draw the diagram. So you just draw a magnetic field. Okay, magnetic field inside the board, just draw it. Okay, then what is it say? What is the condition? That the radius is slightly smaller than mv by qb. That means I can say that the radius is what? Approximately equal to qb, because the word slightly smaller is used. So I can say my radius, okay, my radius, let's just increase this a little bit. Students, please listen to me. My radius and, okay, is going to be this much, and my d, that is the width. Okay, so he's telling here, what they're telling is basically the width, sorry, not r, the width of the magnetic field. Width of the magnetic field is slightly smaller than mv upon qb. But what is mv upon qb, students? mv upon qb is what? Radius. So in this case, in this question, basically he's telling that if the width of the magnetic field is slightly smaller, or in other words, approximately equal. Okay, approximate, slightly smaller means you can say approximately equal also. So width is approximately equal to the mv upon qb, which is basically your radius. In that case, what will be the deflection, students? Can you tell me what will be the
90
deflection?
degree.
Someone said 90 degree. Any other answers? Any other answers? Students, this is a very easy sum, very easy solution. See, look here. Eh, no, no one. Okay, there are chats. Huh? Okay, let me see the chats. Who all have written? So what will happen if the velocity is not enough to overcome the magnetic field in the last case? Wouldn't the circle within the magnetic? Wouldn't it circle within the magnetic field itself? Yeah. 90 degree. Someone said 90 degree. Okay. What will happen if the velocity is not enough to overcome the magnetic field in the last case? I don't get you. I don't get you, Advait. Let me know again. What do you mean
Sir,
actually?
90 degree.
Okay, someone says 90. Advait, what is your question? You can repeat after this, after I finish this concept. Okay, so students, here look here. If I'm saying that this radius here is equal to this, is both are equal in length, then you can simply picture a circle. You can picture a circle where this radius r is basically equal to d. In that case, what will be the point here at which it will escape? What will it be at the point here with this? Going to be 90 degrees. Yes or no? You didn't understand? Look here. Look here. This is what I'm going to say. That if the radius was equal to my width, if it was equal, then how will the charge move? The charge will move from here and it will go exactly like this, and it will escape here. It will escape here. It has become a quarter of a circle. Why it is a quarter of the circle? Because the radius of the radius here is equal to the radius here. The path will complete a quarter of a circle. It will cover a path which is equal to the quarter of the circle, and the angle of deviation is between what, students? Is between what? Is between what here? Can you tell me it's between what? Students, angle of deviation is between what? Velocity and
D.
yeah. So here, this is your velocity here, and the angle of deviation will be theta, which is equal to 90 degree. In other words, you can also say that theta is going to be equal to sine inverse of q b d upon mv. Yes or no? Q b d upon mv. But here, what is the condition? Is that d is equal to r. So if d is equal to r, basically that is also equal to mv upon qb. Okay, d is equal to r. The question here, slightly smaller than mv upon qb. Substitute that value in d over here. So you will get theta equal to sine inverse of qb mv into the value of d, that is mv upon qb. Both will cancel each other, and what remains is theta equal to sine inverse of 1, which is equal to 90 degree. Which is equal to 90 degree. Is this clear, everyone? Okay.
Yes, sir.
Advait, what was your doubt?
Sir, I was asking that if the velocity that we are giving to the charge, if it is not enough to overcome the magnetic force, then what will happen?
But see, any type of velocity, see, that is the thing, no? That is why I done the cases. And in the beginning, I told if q is equal to 0, nothing will matter. But q, if it has even a little bit velocity, there will be a force on it because of the magnetic field, which you can see by F is equal to q v cross b. So it is not possible that even if the velocity is the most minutest in its magnitude, it is still going to have a force, and it will start to move. It will start to move. So I hope that solves your doubt. So anyway, students, is the doubt clear, Azit?
Yes, sir.
Okay. Okay, students, now listen. Next question is a similar thing. Next question is a similar thing, but here, let me read out the question. Find the angle of deviation of the particle as it comes out of the magnetic field. Okay, same thing. Find the angle of deviation of the particle as it comes out of the magnetic field if the width d of the region is slightly smaller than mv upon 2qb. So here, okay, it's written width is slightly smaller than mv upon 2 times qb. mv upon 2 times qb. Please solve this. So I will start anyway. So look here.
30 degree.
Someone said 30 degree. Someone said 30 degree. Right, correct. Okay. So if my magnetic field, if the region of, first draw it, you can draw it like this. And here you can obviously see that if I say this is D and this is going to be my radius R, in the question it is saying that D is slightly smaller than mv by 2 qb. That is what? 1 by 2 times the radius, yes or no? R is mv upon qb, so 1 by 2 times the radius. So I can say that half of the radius is going to be R by 2. Is going to be R by 2. So simply you can apply the formula once you know this much. Once you know this much. Look here, students. My charge is here. My charge is here. If it is going to have some certain velocity, what will it be its path? Will it be able to complete even a quarter? Will it be able to complete a quarter? Quarter can be completed only if I say that this is equal to this. This radius right here, R, will be equal to the radius right here. That is when a charge can complete its full quarter here. But if I'm saying that this itself, this radius itself is like this. The radius only is this much at this point. So in that case, will my charge be able to complete a full quarter? No, it won't be able to complete a quarter. It will only be able to complete a certain amount of arc, something like this. Something like this. The escape velocity will be somewhere here. This will be v, and this will be some angle theta. So how do we find out that theta? Basically, now you know that d is equal to what? D is equal to mv upon 2 qv. Why? Why is it equal to? Because d is slightly smaller than mv upon 2 qv, which simply means approximately equal to. So I said d is equal to mv upon 2 qv. So if I know that, I can also say that mv upon qv is what? R. So 1 by 2 times R. Now, we know the formula theta equal to sine inverse of qbd upon mv. qbd upon mv. Yes or no? D is equal to 1 by 2 times mv upon qb. Apply the formula. Apply it in the formula. So instead of D over here, you'll write 1 by 2 times mv upon qb. So you'll get what? Sine inverse of qb upon mv into the value of D, that is mv upon 2 qb. So that will get cancelled. You'll get sine inverse of 1 by 2, and that is equal to pi by 6. Pi by 6 or 30 degree. So this angle will be theta equal to 30 degree. Theta will be equal to 30 degree. Everyone understood this? Yeah. Okay. So let's go to the next question now. Go to the next question. Next question is a good one. Please mute everyone. Am I audible now?
Yes, sir.
Okay, sometimes there's a disturbance, so it becomes difficult. Okay, anyway, students, listen to me. If this is going to be the magnetic field, okay, question I will tell you right now. If this is a magnetic field and I flicker, I take a charge and I flick it with some velocity v, but I make sure that this has an angle theta associated with it. So you can see this charge here, this charge q is going to be having some velocity v, and it is making an angle theta. So in that case, can you tell me what will be the path? How will the path be in this case? What will be the path of the charge in the magnetic field? What will it be? So will it be circular in nature? Will it be circular in nature? So again, you know that magnetic field is inside. Magnetic field is inside. Okay, and you're basically having a velocity vector going downwards. Velocity vector going downwards. So in that case, apply v cross v. You will get a force in this direction. Force will be in this direction. So if the force at this point of the charge is going to be in this direction, then it will slightly it will somehow move like this. It will move like this. Yes or no? It will move like this. So if it is moving like this, now I have completed one part of the question, that is to describe how it will go. Now the question is, find out what the length of it will be. Find out what the length of it will be. So let me just draw it clearly. So if I'm saying that this is so this is my charge here with a certain velocity theta, and I have already got the path like this. Then can you tell me the approach to find out the length of it? Can anyone tell me the approach? You all can unmute yourselves whenever you feel like. And
For the length of the path.
Length of the path, yes, but what? Yes, I want to find out the length of the path. How can I do it?
The other side will also be theta.
Okay,
It
other
will
side
come
will
out
be
by
theta.
theta d.
Okay, okay. So we can go by a little bit of geometry here. So students, if this is theta, then I can say this is going to be theta. And if this is theta, of course, this is also going to be having some theta. It is going to escape with the same theta angle over here.
Sir, we
In
can
that-
also use the formula of theta equal to L by R.
Yes, solid angle. Yeah. We are coming to that. Listen. So if this is theta, okay, this is going to be theta. So in that case, students, listen to me. Let's consider this to be a part of a circle. Let's consider it to be a part of a circle. Let's say the origin is somewhere here. In that case, I can say that it's going to be like this. It's a part of a circle. And you can see that my charge over here, that the charge is having a path in this direction. So you can see if this is theta, students, if this is theta, but forget that, what will be this? What is this, students? Is this a right angle? Yes or no? 90 degree?
Yes, sir.
So, and this is theta. So then what will be this?
90 minus
90
theta.
minus theta.
90 minus theta. Students, please keep telling me. Okay, if this is 90 minus theta, students, then there is also another 90 degree here. Where? Look here. If this is 90 degree here, this is also an angle theta here. Look here. This is also 90 degrees. Okay. So what will be this angle then? Okay. What will be that angle? So see, this
90
entirely
minus theta.
is going to be what? 90 degree. This entire angle here 90 degree minus what angle is here? 90 minus
90
theta.
minus 90 minus theta.
So that is going to be what, students? 90 minus 90
Theta.
plus theta. So it's going to be equal to theta. So this is theta. Okay, that is what. Has everyone understood this? Students, please tell me. Has everyone understood this geometry at least?
Yes, sir.
Okay. So if this is theta, students, if this is theta, we know this is also going to be theta. Yes or no? And if you draw a bisector here like this in this form, then we know this is forming what? a right angle triangle. So a right angle triangle where you can say this is 90, this is also going to be, if this is theta, this is also going to be theta, this will be theta, this is theta, this is 90. Then let's say that I have a radius here. This is the radius of the circle, isn't it? It's going to be like this, radius of the circle. In that case, what will be this angle with respect to the diameter of the circle? Will it be pi minus 2 theta? Yes or no? Pi
Yes,
minus
sir.
2 theta. Okay, students. So this angle right here, is going to be pi minus 2 theta. So now we have found out this, we can apply the concept of, what? We can apply the concept of angle. Theta is equal to L by R. Theta is equal to L by R. We are interested in finding out the length. Yes or no? Theta is equal to L by R from where I got? Remember the form? You remember this? Where I
Yes,
said
sir.
that if this is theta, this is the length and this is the radius, then we can say the length subtends an angle theta, and it can be written as theta equal to L by R. This was when we did plane angles and solid angles. So if I know this much, then I can say that length is equal to theta into R. Theta is here pi minus 2 times theta into R. So this is my length. This is the length of the path of a charge in a magnetic field. Okay, in a magnetic field. Hope you have understood this.